Hello and welcome back. Okay, in the last video I added this resistor ladder and used that to implement volume control. I used the AND gates here to stop the clock when I set the volume to 0, well 15 in this case. And then I used the volume to implement a basic ADSR envelope, so now the tones in my music sound just that little bit better shaped, but it's not perfect. If you listen carefully, you can hear a rattle in the background. And that rattle is caused by these two latches here, one which controls the low 8 bits of the frequency divisor and one that controls the upper 4 bits and the 4 bits of volume. And it's not possible for me to set those two registers simultaneously. So there's always a chance that I set one and then the counter loops around, loads the value in, and it's got an incorrect value for that pulse. So today I want to see if I can solve that and clean this music up a little bit more. So this is how the circuit currently works. We've got two of these 574 latch chips. Now the first of these is hooked directly to the main bus, and the second is daisy chained from the outputs of that. The load line for the port goes to the load line of both those chips. So then when we load, the data that's currently in this one gets transferred to this one, and whatever's on the bus comes onto the first one. So that way we can output data from both of these just by doing two sequential loads. And then of course we get the problem we're worried about, where the first time we load, we've got the previous low data coming out here and the new high data coming out here. And then we have to load again before we've got the correct data coming out the output lines. Now this daisy chain is not the way it would normally be done, so let's look at what we might normally do, which is to use a second I/O port for the second half of the output. So here we've got the load line for a second I/O port hooked into its own 574. We've lost the upper component here, and now we'd do the operation by doing two separate loads to the two registers. So we don't have to worry about stepping the data forward in the chain. And if the note's close enough that, say, the upper component is shared between two notes, maybe we'd get less glitching this way. But fundamentally, we've still got the same problem where one of these registers will update and then the other will update. So how could we solve that? This is how I suspect most devices work that have a pair of dependent registers. So here's my fault. We go with a very similar configuration as the last form, but we have an additional latch chip. So when we load the low data, it goes into here, and then we output the same control line for the high portion into a second latch chip. Now think about what happens. We load the data for the low half here, then we load the high data here, at which point simultaneously the data is transferred from the holding latch into the output latch. And that would solve the synchronization problem because the outputs all change simultaneously. Unfortunately, the whole method I used before of daisy chaining low and high on the same I/O port is because I don't want to use more than one I/O port for the audio subsystem, because otherwise I'm going to have to build a whole new I/O system in order to handle additional peripherals. So let's look at another idea I have for doing it. So we're back to the shift register type configuration. Don't need the second I/O port control lines anymore. But to get the synchronization, I'm going to introduce a second pair of latch chips. I'm going to take those from the shift register pair, and then we'll output from those. Now we need something to drive these. Any old control line will do, because this is just going to control when the data is transferred from these over to these new output driving latch chips. So what I'm going to use is I'm actually going to use the read line, which I don't have another use for, but that's a convenient control signal that's already in the wire going to the audio device. Now the big reason why I'm picking this daisy chain latch solution is because I'd like to add more than one channel to my audio system, and so if I was using separate ports for each byte, I would go to two channels. I'd need 4 I/O ports, whereas with this, just the one I/O channel is enough to handle as many ports as I want. I just have the added complexity of outputting data for all of them at the same time. Let's build it. Right, so I think the breadboard layout I've been putting together here is not going particularly well. Now normally I try and plan this out so I don't have to do big reorganizations, but it's warranted on this time. Now I've got these 2 latch chips here and I need room for 2 more. I've also got some bits of circuit here which are going to be shared between the 2 channels. So the main crystal oscillator, the set reset latch here, and the 4 input AND gate is simulated by using 3 of the 2 input AND gates on this 74LS08. And I've received now some of these 74LS21s, which are dual 4 input AND gates. So I will only need half of one of those. So these 2 chips and the oscillator I'd like to move onto a central breadboard and see if I can fit the rest of this circuitry with the 2 extra latches onto 2 breadboards. This one at the top with the black lines is one of the BB830 boards. Hoping to get a whole bunch more of these before I start the video project. Okay, so I've put my latch chips in. Now I'm going to make the left to right pairs the shifted version and the permanent storage. So on the right hand side here is going to be my big shift register, so the bus will clock in data from here and then the latch for use will go over to the left. So I need to connect these vertically. So it's the ground going in. Ground over here is going to be tricky, but we also want the output enable permanently on. I'm trying to get these chips right over to the edge. And I can use these wires to get the ground line in. The right pair and then the left pair need to get latched simultaneously, so I need to connect together their load lines. My bus input will be here. I still want the display. You can always tell the common pin on these resistor arrays by the spot. Now I need to connect the outputs from the shift register D latches into the use D latches. Okay, these ones are going to be tricky, so I'm going to cheat. Let's give it a test. Here's the bus test circuit. So this can generate 8 bits and output it here, conditionally asserting it onto the bus. We just want to assert. But I've also got some control lines here that look a lot like the ones my CPU can generate. Well, that was promising at least. Let's set the top 3 bits. I'm going to latch that. So that should be loaded into this latch chip here. Then I'm going to invert this. So now when I hit the load button, the previous pattern should be loaded into this chip, and then this latch chip should take this new pattern. And then when I hit the second signal, the low and high portions of the overall number we've got should be transferred into the output registers. Perfect. Nice one. Okay, so now I'm going to need to start bringing some circuitry across from here. It's suddenly started getting warm. I've not put it in the wrong way, have I? Yes, I have. Hopefully that still works. So I'm going to pack my 193 chips in here as close together as I can. These are the lines that connect together the parallel loads. These are countdowns, or borrow connected to countdown. For this one, borrow went to count up. I suspect these might be a bit easier to tidy up than they would have been on the old arrangement, but I'm going to use the hookup wires just to get the data connections in quickly. Right, so the NAND chip here is forming a set reset latch using 2 of the 4 NAND gates, and I want to do 2 set reset latches, one for this first channel, and I'm going to put the second channel above. So I actually want to use the 2 lower NAND gates here. So I'm going to kind of fix that before I move it so I don't lose track of what I'm doing. So it's the clock going into that input. We could actually swap that over and move that there. So that's the output of the second latch going into the second input of the first. So, okay, so the output of this first one is currently going to the second input of the second one. But it's going to be more convenient for me to do a single link there. And move the current first input, which is the clock, to there, because it's also going to be closer to where it's needed. Alright, so it's the clock directly into the SR latch. Hop that straight across to where it needs to be for the second one. Here's the set. I believe that was Q3 here. That ground is in the wrong place. So then reset comes from the clock. Then the second output is actually driving the parallel load. Okay, I think that's all. Right, now we need to feed our 4 volume outputs into our exclusive OR gates. Okay, so that's all the second inputs wired together. Just trying to match the same ordering over here. Okay, so that's the inputs. We need the outputs. I've actually got a suspicion I might do better with a higher value resistor here. Right, this is my voltage divider that creates the virtual ground in between the power rails. It needs to go there. This output stage I'm going to rework heavily in the next video, I believe. Okay, now what are we missing? These 4 outputs go into the lower 4 bits of the resistor ladder. I'll have a crack at tidying these up as well. Now I need those 4 bits to go to the AND gate, which I was going to switch in one of these 7-4 LS21s. Now the order of these doesn't actually matter. Whether or not they reach does. Okay, well those were 1 bit off. It's going to be a miracle if it still works. So much easier than faffing about with free 2 input AND gates. Now that's the reset line into the final counter, and that should be everything. That's a lot neater. I've got all of this space here to work on the output. In theory I get a tone if I output that to both. Okay, small break there to get the scope set up. Okay, we should be getting a tone from this. Okay, so there's our clock, 1.8 megahertz. And that's not going into the countdown. So now why isn't this chip counting? Right, so we know the clock's coming in. We've not got a clock coming out, so parallel load is coming from there. I may need to apologise to people. I think that was kicking out a high-pitched tone. Or was it? That is the parallel load getting hit at the full frequency. And that's because I've wired this all wrong. I've wired what should have been the parallel load inputs into the outputs from the counter chip. So this is 0. Good thing I didn't spend that time tidying these up. 1, 2, 3. Okay, the load is still happening at 1.8 megahertz, so that's still not right. I was supposed to be setting the set reset latch on the increment of this counter. So now the output is supposed to be there. So next mistake is my reset for suppressing it based off the 4 input AND gate on the volume. It's going to the wrong line. I was taking it to the parallel load, it needs to go to the reset. So now the input to there is 7.14 kilohertz. The output's supposed to come from there. So that's 446 hertz, which is the final divide. And I haven't actually hooked the output up. So I'm going to steal this green wire from my probe. That belongs in there. Yes. Don't like the sound of that. So this is me connecting and disconnecting the ground of the oscilloscope. I'm going to plug in my battery pack. And then unplug the ground from the oscilloscope, and it doesn't go bad. My USB power pack is kind of noisy, and I've realised that a little while ago, which is why I started powering my CPU off the power bank. But I don't think it was really causing me any significant problems until I had the UART that was joining the grounds between this and my PC's USB. But I think the extra little bits of frequencies being chucked on here are modulating the sound I'm getting. Might need to look at ways of cleaning that up. Okay, I think it's time to plug this back into the CPU build and see if it's actually done what we thought it was going to have done, but I will need to do some coding first. Right, so power ground. Then the yellow line is the main load command, and green is the assert, which is the one we're going to steal for triggering the latch. We also don't want to do that straight away. I want to test this, and I'm going to try by doing that. So if I trigger that data move from this clock, it will basically happen instantly whatever we do. So that means if everything else is working, this should work as the old circuit worked. Well, it's not working. Oh, haven't hooked up the bus. Okay, this is a very old cable. I do know some of my oldest ones were a bit dodgy. Hopefully this one's okay. Now it won't do anything because it's triggering the loads, but the data's never getting copied over. So we need a code update. Right, so we output the 2 bytes. Now that's not going to assemble because that instruction doesn't exist. Now we are getting very low on spare instruction slots. That assembles now, but we need to add it to the control ROMs. Of course, this is going to be reading a byte from the audio unit, which we're going to use as a trigger for the data handover, but we're not actually going to be putting anything on the bus. Has anyone got any ideas on what we can put on the bus there? Post them in the comments. I've got a few thoughts. So all this instruction does is it orders the audio device to assert to the bus, which is the signal for that is the trigger we're going to use, but then to complete the in operation we're just loading register A from the bus. So control ROM 2A has changed, the other three are constant. I think that's working perfectly. Now the problem is the tune is starting to be let down by the fact that we've only got one tone at a time. Now the whole kind of ADSR envelope we added in the last video means that doing that, the kind of rapid note switching arpeggio, probably isn't the right thing to do to make the sound better. So in the next audio video I'm going to add that additional channel, and I think that's going to lift this tune to the next level. Now, the tune I'm using here is Für Elise by Beethoven. I particularly like some of his work, and one of the regular viewers on my channel, Edge Effect, posted today to remind me that today is actually the 250th birthday of Beethoven. So happy birthday, Beethoven. Well, I really hope you found this interesting. This is probably the smallest audio change in any of the audio videos, but just taking that little crackle edge off it, I think has moved us to the next level. And of course we've got the base functionality we need now and the breadboard organisation to stick an extra channel on here with 2 additional breadboards. That is really going to move this forward. Thanks a lot for watching. Hope you found it interesting. I'll see you again soon. Goodbye.